clock is correct, then it is time to start. All right, are there any questions? Let's get started. So where we left off last time is we were talking about low mass stars, and today we're going to finish talking about low mass stars, particularly kind of their whole life cycle, not just their time on the main sequence, but how they die. And the rest of the lecture today will be about high mass stars, because there's two. Of course, stars in actuality have a range of masses, so it's not quite as simple as just talking about low mass stars and high mass stars, but I think that gives you a shot at covering the two main extremes of what happens. So, and as you'll see, there are kind of two distinct possibilities: low mass stars end with producing a white dwarf, whereas high mass stars can end by producing a supernova and then a neutron star or a black hole. So as a little bit of review, when we talked about a low mass star, we're talking about something in the range of our sun, our own sun. One solar mass is a good example of a low mass star, and its life cycle is in the range of 10 billion years. Okay? So the first step is this process that we talked about last time, about starting from a nebula, right? Dust that collapses, and that process is just a tiny fraction of its overall life, about 30 million years. At that point, it forms a protostar, we say, before entering number 2 here, where it enters the main sequence. What does that mean? That means that it has begun fusing hydrogen to helium, and its thermostat has kind of reached equilibrium. It's now fusing hydrogen to helium, producing new energy that's pushing outward, and it produces kind of a stable size. So at that point on the HR diagram, it has a luminosity and a temperature that places it on that main sequence line. In a low mass star, when it fuses hydrogen to helium, it's mainly through what we call the proton-proton cycle. Hydrogens are made of a proton surrounded by an electron, and a plasma in the sun. What we mean is we just have a bunch of protons flying around and separate electrons flying around. And if protons hit each other hard enough, which requires a high temperature, they snap together. Okay, and they snap together, ultimately forming helium. After about 10 billion years, you enter a phase where the helium is building up inside this low mass star. Okay, hydrogen is starting to run out. It hasn't run out yet, but you enter kind of the end of life phase where the star on an HR diagram exits the main sequence. It starts moving, it starts getting larger and redder, and it becomes a red giant when its core has been replaced by helium. That helium that it produced when it fused hydrogen, it produces a big core of helium that's not yet fusing. It's just, we say it's inert. It's just sitting there, and it kind of breaks the star's thermostat. We'll talk more about that today. So the star kind of balloons out, gets redder, and starts fusing more and more rapidly, and a shell around that helium. Next, there's a stage where it does get hot enough to start fusing helium. Now things are going very, very rapidly. It's fusing helium. It only lasts another 100 million years or so. As it then, its thermostat breaks again, as its core begins to be replaced by carbon. But that's it. For a low mass star, it never gets hot enough to fuse carbon. So ultimately, it sheds off its outer layers once it runs out of fuel, creating a nebula out of which stars can form in the future, and leaving behind a white dwarf, which is just kind of an inert, hot but small, dead core of the star made out of mostly carbon. So that's the overview of what we've been discussing about small low mass stars. And right, this was the HR diagram representation. So a star like our sun is here, and then it goes through this process that we just described. And I can do it in a little bit more detail because this is actually around where. Okay, I'll go through it a little bit more detail after we talk again a little bit about. So this is, I think, where we left off last time, where I was going to actually start explaining in more detail this concept of what happens when the core of a low mass star starts to be replaced by all that helium that it's producing, and we say its thermostat breaks, and that's where it starts to leave the main sequence for the first time. So this is what we see when we look at star clusters. Remember, we talked about, you kind of see the stars exiting the main sequence. What we see is they just get larger. That's moving to the upper right. They get redder, which is moving towards the right, and more luminous as they move up in the HR diagram. And so what we see is that as a star exits the main sequence, say it becomes a red giant, that's because it's getting redder, it's moving to the right, and it's getting more luminous because it's getting larger. The surface is cooler, it gets redder, but overall it gets so much larger that it's emitting more light in total. Now, yeah, so here you have a star on the main sequence, okay? It's fusing hydrogen in its core to helium. But where does all that helium go? It's heavier than hydrogen. Eventually, it starts to accumulate in the core. So you have this inert helium core, and we enter a stage where you start fusing hydrogen in a shell around that core. Okay? Now, the problem with that, you want to call it a problem, is that normally in a star, if the, and we call this its thermostat, if the core starts to get too hot, the fusion actually starts to accelerate. And that would be a problem for the star, except when it gets hotter, it can expand and cool off, and the fusion decelerates. And so it's kind of self-regulating. But once the core is made of all helium and it's fusing in a shell around the core, that core can't expand or contract. That core is like a hard wall. It doesn't contract due to degeneracy pressure. And so the thermostat's sort of broken. Kind of, it just gets hotter and hotter. And this is why the end of life of a star happens so quickly. It's fusing hydrogen more and more rapidly. It's hotter in the core. So the star kind of pushes outward and becomes a red giant. Overall, it's more luminous. It's emitting more energy. It's more luminous because its radius is increasing so much that from the Stefan-Boltzmann law, overall, it's emitting a lot more light. Okay. So it might start off looking like this, and to scale, right, it might end up looking like this during the stage. And this is what we see. Here's an example of actual a star cluster where we've drawn all the stars on the HR diagram, where we can actually see this looks like the star cluster is about a few billion years old, and we're seeing stars kind of like similar to our own sun beginning to exit the main sequence. We call this the turnoff point, where they exit the main sequence. They become subgiants as they begin to, their core begins to fill up with helium. Then there's a period, so they move up here, and then there's a period where they do what's called a helium flash. That's the point where suddenly they get hot enough in the core that they can actually begin fusing helium. So they were just fusing hydrogen, now they're fusing helium. And when they fuse helium, they start to move a little bit back towards the main sequence, because now it's almost like it's a main sequence star that instead of just fusing hydrogen in its core, now it's fusing helium. And its thermostat is regulated again until now carbon is building up in its core, okay? And at that point, for a low mass star, it can never fuse carbon. So that's kind of the end, when the core builds up so much carbon that you're running out of fuel in these shells. You're at a certain point, you have a shell fusing helium, another shell fusing hydrogen, and it burns up the remaining hydrogen and helium in just about 100 million years before finally dying and becoming a white dwarf. These are all the dead stellar remnants from these low mass stars. or high mass. We'll talk about that high mass stars leave stellar remnants, but we don't see them as white dwarfs. They look a little bit different. So we'll talk about those later today. So one thing is, right, we talked about how you fuse hydrogen in stars. How do you fuse helium? Well, helium is made of 2 protons and 2 neutrons. Looks kind of like this. It's a nucleus composed of 4 things: 2 neutrons, 2 protons. So we signify it like so. 4 is the total mass, 2 represents the 2 protons. And we call that thing an alpha particle. We call that because it happens to be very stable. It's a stable particle, meaning if you take a bunch of protons and neutrons, they like to form little particles, these groups of helium that we call alpha particles. And these alpha particles, or helium nuclei, can form carbon. So when they fuse, the way they tend to fuse is 3 of them fuse together at once to form carbon-12. And they produce energy. So a star can produce energy through helium fusion, producing carbon. So this is what happens in a low mass star. And this is where most of the carbon comes from, right? That life is made out of. What is the triple alpha process? That might sound like a fancy term, triple alpha. It's the process where helium is fused in stars to produce what? To produce carbon. Okay. You can remember that maybe by thinking like how many helium nuclei would you need to fuse to form carbon? Well, you need to fuse 3. Each helium nucleus has a mass of 4. 3 times 4 is 12. And you should have in your memory carbon-12. 12 is the mass of carbon. So 3 heliums together make 1 carbon-12. That's how it's formed. Any questions so far? So we're still talking about low mass stars here, and I'm getting towards the end of the low mass star's life. There's a point when the helium that was inert in the core heats up. Okay, that is, this helium core has a tremendous amount of pressure pushing it in. Now it's degeneracy pressure that's keeping it from collapsing completely. But as that pressure pushes on it, it heats up, right? And once it reaches about 100 million degrees, that's now hot enough finally for these alpha particles to snap together and form carbon through fusion. Now, the helium fusion rate goes really, really quickly until the star's thermostat becomes regulated again, okay? Until the core can expand now that helium is being fused. It's no longer just a degenerate inert core of helium. It's now a plasma. It now can expand to cool itself off a little bit until it reaches equilibrium, just the same way we talked about with hydrogen. So for about 100 million years, well, for about 1 billion years, at this point, it's about 100 million years, this star is kind of back to being a stable star. It's just not, instead of being on the main sequence fusing hydrogen in its core, it's fusing helium in its core, okay? But the whole process is going more rapidly because it's much hotter in the core of a helium fusing star. So the whole fusion process is happening much more quickly. It's going to run out of fuel more quickly, and it's going to convert all that helium into carbon, inert carbon more quickly. And whereas it's about 30 million degrees in the core of a hydrogen fusing main sequence star, it's about 100 million, it's more than twice, 3 times as hot in the core of a helium fusing star. And that's why it's going to run out of that last amount of energy pretty quickly. Okay, so now that we are in the end stages of the star's life, where it's fusing helium in the core, it also still has some hydrogen around, right? The hydrogen didn't get used up, right? But this process started because the core was replaced with helium that had built up, and that helium began fusing. So you still have you have the helium core fusing, and now you also have a shell of hydrogen fusing. Okay, and at a certain point, carbon now begins to build up inside this thing. And you just, as before, you have had an inert core of helium, here you have an inert core of carbon. This is what will become the white dwarf. And in a low mass star, the carbon never fuses. It can never get hot enough to fuse. So what happens instead is just the thermostat breaks again, because this carbon core can't change size in order to, well, can't expand to lower the temperature of fusion. Instead, you just have these, a shell, we call it double shell fusion, a shell of helium, and then a shell around that of the lighter hydrogen, both fusing very, very rapidly as the last helium and hydrogen fusion, kind of the last gasp of the star is used up. And this process ends when the star runs out of fuel completely. Basically, what happens is suddenly there's not the pressure that was previously there, produced by heat in the core, to keep the star stable. Okay, and so what happens is you have a collapse. You have a collapse in the star that all at once, suddenly, a tremendous amount of gravitational potential energy has to be, as it collapses, has to go somewhere. And what it does is it produces a small explosion that blows off the outer layers of the star, producing what we call a planetary nebula. This has some hydrogen and helium still mixed in, along with a little bit of carbon. And this is the sort of thing that can go into produce a solar system or another star. The term planetary and planetary nebula, though, is just kind of historic. This is just what we call these things, planetary nebula. And what's left behind is this inert dead core of solid carbon called a white dwarf. And this thing initially is very, very hot. It's small, so it's not very luminous, but it starts off blue hot. And why doesn't it collapse under gravity? Well, this is degeneracy pressure. It's the same thing keeping the Earth from collapsing. It's what keeps things solid. Remember this quantum mechanical effect that electrons and atoms don't want to overlap, so it keeps things kind of solid. So that's what keeps this core from collapsing, is a solid core of carbon, very dense, very strong gravity, very hot, but it has no source of heat, so of new energy, so it just slowly cools off over time. Here are some pictures from the Hubble Space Telescope of various, often very beautiful planetary nebulae from the death of low mass stars. So this is kind of what our own sun will produce about 5 billion years from now. There's a couple up close that are particularly striking. There's the Helix Nebula. All of these, of course, are relatively nearby in our own galaxy. That's why we can see them with such striking clarity. There's the Butterfly Nebula. And what's left behind inside these things? In the center, what's left behind is something that's hard to see. It's not glowing very bright. As you can see, you mostly just see the nebula here. That's because these things are not luminous. They're very small. And what's left behind is a white dwarf. It's very small, initially hot, but just cooling off core of carbon. So what happens to the core of a star after it ejects a planetary nebula, after the last death throw of a low mass star? You're left behind with a white dwarf called white because it's like white hot, as opposed to a brown dwarf. But it does cool off over time, so it's not going to stay white hot forever. So here's a good opportunity to kind of just go through this whole process again, but with some detail on an HR diagram. Here's the HR diagram I've shown before, kind of giving this overview, but this has a little bit more detail, so let's go through this one. So here's an HR diagram. Remember, the HR diagram on the y-axis has luminosity. The x-axis is the temperature, or the surface color temperature, or color of the star. And the main sequence, that is high mass stars up here, low mass stars up here, goes from the upper left to the lower right. Low mass stars are kind of the lower half of stars in this region. And the sun is kind of a typical example. So the sun is going to be on the main sequence for about 10 billion years total. But then there'll be a time, about 6 billion years from now or so, 5 or 6 billion years, when the core of our sun will start to have built up a lot of helium. It will have gotten so much helium in its core that it's going to start to disrupt the thermostat of our sun. And the sun is going to start to get much larger. Okay? It's going to eventually swallow up some of the inner planets. It's going to get so large. And it's going to get redder on its surface and overall more luminous. And there's for a large part of this time, it's burning hydrogen in a shell, we say, around this inert helium core. Again, it's kind of moves off the main sequence because its thermostat is kind of broken. That core is no longer a core where the fusion is happening that can expand and contract to meet the, so that if the fusion rate goes up, it can expand and cool off and lower the fusion rate. It's not in equilibrium anymore because now the core can no longer do that. That hydrogen that's fusing around the core is pressing on the core, which just heats the core up. The core just keeps getting hotter and hotter. And that hydrogen fusion in that shell just goes faster and faster. And so this star just balloons up, getting hotter and hotter until the core eventually reaches the point where helium is hot enough, about 100 million degrees. Helium is hot enough now to fuse. You get what's called a helium flash, as suddenly that whole core is fusing helium. And then it kind of settles back. So it moves back this way, kind of settles back more closer to the main sequence back, because now it does have a thermostat. It's just it's fusing helium in its core instead of hydrogen. We call this the yellow giant phase, when it's moving back towards the color and brightness of the main sequence stars. But doesn't take too long now because this is all happening more rapidly, for now the helium that's producing carbon through the triple alpha process to build up an inert carbon core, which again starts to break its thermostat. And so what it does is it turns around. It starts going and becoming a red supergiant, where you have helium in one shell around the carbon and hydrogen in another shell around the carbon, both kind of using up the remaining hydrogen and helium very, very rapidly, because they're getting hotter and hotter and hotter. So just the last 100 million years is this very last quick burn of the star as it gets bigger and bigger and expands outward in the red supergiant phase. Finally, kind of runs out of steam, runs out of hydrogen and helium, ejects its outer layers in a planetary nebula. There's some of those beautiful pictures we showed you. The core shrinks down to form a white dwarf. And because there's no fuel to keep the white dwarf hot, it does cool off over time. So it kind of moves this way over time, becoming less and less hot and getting less and less luminous. And most of this white dwarfs you see are way down here. They've cooled off to the point where they're very hard to see because they're so small. And even though they're initially very hot, they're still so small that they're just not very luminous. But you can tell because they're down here. They're usually about a tenth as bright as the sun, or less. and all the times for this, and it's all different for different mass stars, but for example, the Sun-like star spends about 9 or 10 billion years on the main sequence, about 1 billion years in a hydrogen shell around inert helium, then about 100 million years as a yellow giant here, before just a few more million years becoming a red supergiant and producing a planetary nebula, leaving behind a white dwarf. Any questions about the story we've told about the life and death of a low mass star like our sun? Okay, so here's the diagram from the book showing the same thing, just with a little bit less detail. Okay, so in summary, low mass star. You initially have the star in the main sequence. That's where it spends most of its time fusing hydrogen to helium. But at a certain point, it does start to run out of hydrogen. The first thing, though, that happens is it builds up too much helium in its core, and you get a shell of hydrogen fusing, and you get a red giant. But then eventually you do have helium fusing in the core. We also call this the horizontal branch. But you can just think of it as the yellow giant phase, or the phase where just helium is being fused in the core. Finally, you have a double shell fusion where you've built up carbon in the core, helium is in one shell, hydrogen in another shell, and that's the last phase because carbon can't fuse in a low mass star, it just can't get hot enough. And then finally, the death of a low mass star sees the ejection of most of the remaining material, which still is mostly hydrogen and helium, but some little bits of carbon in a planetary nebula. And leaves behind this tiny, initially white hot, but hard to see white dwarf. And that's going to just stay a white dwarf until the end of time, at which time it will cool off to the point that we tend to call it a black dwarf. It'd be very hard to see. So I do want you to kind of know the main sequence, right? Like what happens first, then what, then what. And the main phases of the sequence is that you have a protostar. That's the name for what you have when you have this contracting nebula heating up material that hasn't yet begun hydrogen fusion. Then it enters the main sequence, then it becomes a red giant, and then finally its last relic of being a star till the end of time is a white dwarf. Although it does cool down to the point that it's no longer white, and we then call it black. Any question at all about low mass stars before we talk about high mass stars? I'll let you think about that while I get a drink of water. Okay, well, here's the overview of a high mass star. And again, high mass stars can have a whole range of possible masses. I'm just taking one example mass to illustrate the point. So we'll consider, for example, a mass of 25 solar masses. Remember, a star can be up to 150 solar masses, in which case all of the process I'm describing basically just goes faster. Okay? So in a 25 solar mass star, first you have the collapse of a nebula to a protostar. That's just happening faster than for a low mass star. The larger amount of mass means it can contract faster. Then you have a main sequence star that instead of burning, say in the JKM part of the stellar spectrum, is more towards OBAF. We might call it a blue main sequence star, right? It's so hot that it's kind of bluish in color. And it's fusing hydrogen to helium, but instead of through the proton-proton cycle, remember there's another cycle that comes in at a little bit of a higher temperature, called the CNO cycle, where it uses some existing carbon, nitrogen, and oxygen as catalysts, and the hydrogen snaps onto the carbon, and then snaps onto the nitrogen, and then snaps onto the oxygen to leave behind a helium. And then the cycle can begin, and a carbon that can begin the cycle again. But at the end of the day, you're still fusing hydrogen to helium. And in a 25 solar mass star, this all its whole main sequence life is only about 5 million years. So this is a very short-lived star, and that's because it's burning through its fuel so quickly because it's so hot in its star because it's so massive. And its core, so hot in its core because it's so massive. Next, it becomes a red supergiant. We call it a supergiant because it's just very large because it's a large mass star. But this is the same concept as for low mass stars. That the core is now helium, which is inert, and so the thermostat is broken, and so you have hydrogen fusion in a core, right, in a shell around the core. So the thermostat is broken, so it gets hotter, it balloons out, becomes what we call a red supergiant. Then the same next stage as for a low mass star, the helium in the core gets hot enough to fuse, so now you're fusing helium. And you're building up carbon, and then you enter a phase where you're fusing helium and hydrogen in shells, just like for the low mass stars. But the difference is that for a high mass star, it gets hot enough so that you can fuse the carbon too. In fact, it gets so hot that you can fuse everything possible in what's called a multiple shell fusion supergiant. It only lasts for about 10,000 years, but this is where most of the elements come from. Okay, most of the stuff that we see on Earth is because in one of these large high mass stars, you can have not only carbon fusing, but oxygen and so on, all the way up to iron, which we'll talk about. Another place some elements can form above iron, as we'll talk about, is supernova, which is the kind of catastrophic explosion at the end of life of a high mass star, and it leaves behind a neutron star or a black hole, which is something we'll talk about in detail in a future lecture. So just like a white dwarf is the relic left behind from a low mass star, either a neutron star or a black hole is left behind by a high mass star. So this is what the high mass star kind of looks like on an HR diagram. Remember, it's the upper left here that represent higher masses. So this is these are the sort of stars we're talking about when we talk about high mass stars. And here's some examples. Here we've been talking about, let's say, a 25 mass high mass star. So say this example, and it does a similar thing when we talk about it first having a shell of hydrogen fusing and going along this way, and then going back as the helium fuses, and then going back to the right as the you have double shell fusion and so on. The main difference is that you see that it's kind of flatter here. It's moving more horizontally. That's because these stars, while it is getting redder, it's moving to the right, and it is getting larger. If you move to the right, you also have to get larger. So because in general, if you move up diagonally to the right, you're getting larger. But a star that starts out really large can't get much larger. So that's why generally these lines stay kind of flat. They're not getting too much larger, mostly just getting redder. Although they do get larger. Okay, so a couple reminders. We talked about this before when we talked about our sun. But in our sun, this doesn't happen much. It's mostly high mass stars where this is most relevant, where you can get hydrogen fusion by, instead of just directly fusing 4 hydrogens together, okay, you first fuse a hydrogen to carbon, that's the C in CNO. Then you snap a hydrogen onto carbon again, this time carbon 13. Then you snap a third hydrogen onto carbon, nitrogen 14. Then you snap a 4th hydrogen onto nitrogen 15 to form carbon 12 plus helium. This carbon 12 goes back to the soup to start the cycle over again. But now you've got a helium atom, okay? And you start in this way, removing hydrogen, fusing it and accumulating more and more helium, which is heavy, so it falls down into the core. Right? This is a good opportunity to have a poll question just to make sure you're familiar with what the C&O cycle is. Okay, what is the C&O cycle?
Carbon, carbon, nitrogen, oxygen.
I'll give you 10 more seconds. Okay. So it's interesting. Most of the people who answered quickly did get the right answer, but ultimately, the answer that won out is a wrong one. So people mostly said the process by which helium is fused into carbon, nitrogen, and oxygen. Well, let's go back here. No, this is the main. So this is what happens on the main sequence for a high mass star primarily. It is how hydrogen. So on the main sequence, we're talking about hydrogen fusing into helium. But it's called the C&O cycle because we have hydrogen, as we saw here. Hydrogen fusing onto carbon, nitrogen, and oxygen. Those are kind of floating around acting as catalysts. The hydrogen can snap onto carbon, snap onto nitrogen, snap onto oxygen, until you get 4 that have snapped on to produce a helium. So it's how you produce helium. And the answer here was C, a type of hydrogen fusion that uses carbon, nitrogen, and oxygen as catalysts to produce helium. It's not a way that helium itself is fused. Are there any questions, especially since about half of people got that one wrong? Okay, this is the main way that stars on the that massive stars, much more massive than the sun, get their energy when they're on the main sequence, when they're fusing hydrogen. Now, so in a low mass star, this isn't relevant. In a low mass star, you're fusing hydrogen to helium, helium into carbon, and then you're done. But in a high mass star, it's hot enough in the core that you can actually fuse everything that's possible. Okay, and we talked about this. It's called the curve of binding energy. How much energy can be given up when you snap together, when you fuse atoms? And this is better understood maybe if I flip this around. And you can think of this as the excess mass per proton or neutron in one of these things. And remember, you can convert mass to energy. That's how you get energy out of a star. And so what you see here is that there's a lot of energy in hydrogen if you can fuse it into helium. You're converting a lot of mass. So all of this mass between here and here gets converted into energy if you can fuse hydrogen into helium. Okay, but you can also get lots of energy out, less, but a lot of energy out by fusing helium, and then fusing carbon, and fusing oxygen, and fusing silicon, and everything. You keep fusing stuff until you reach the bottom of this curve where iron and nickel is. But iron and nickel are similar at the bottom of the curve. We usually just say iron now. at the very bottom of this curve, we have iron, and you can't fuse anything past iron. Why? Because it would take more energy. Instead of getting energy out, it would take more energy. And so we can produce elements past iron here, but not during the life of a star when it's creating energy. You can get some of these elements out here during what is called a supernova, which we'll talk about later, when the star is outward with huge amounts of energy. Some of that energy can go into creating these heavier elements. But inside the life cycle of a star up until the supernova, when it's fusing things in its core, you can fuse all the elements up to iron. And that's where the elements come from, for the most part, up to iron, okay? Which are, as we'll see, the most common elements. By the way, what this curve of binding energy also shows is something else interesting, which is that if you do happen to have something to the right of iron, like uranium over here, you can get energy by doing the opposite, by fission, by breaking the atoms apart. Instead of fusing, you can break them apart and get energy. As you move to the left, you get energy until, again, you reach the bottom, until you reach iron. Now, so if I were to ask which element has the lowest mass per nucleon and therefore cannot release energy by either fusion or fission, it's iron. Iron is the end point of either radioactive fission of uranium, and keep fissioning and fissioning until you reach iron, or if you have a star that's fusing things, it'll end when it reaches iron. And so when we have a really high mass star and it doesn't stop at carbon the way it does for a low mass star, you can eventually, the core gets hot enough that you're not just fusing carbon, you're fusing oxygen, you're fusing neon, you're fusing magnesium, silicon, and eventually you're just building up a core, an inert core of iron, and the fusion stops at iron. You can't keep fusing away. Eventually you reach iron, and that's why the star eventually dies, and it builds up a core. Now, there's a few interesting things we can talk about. So, for instance, what elements are mostly going to be? So, this is kind of interesting because then we can compare it to what we see all around us, because all of the stuff around us formed inside stars. So, the most common processes, and it's because alpha particles, hydrogen, helium is so common, is for starting at carbon, because so hydrogen to helium, helium to carbon. What next? Well, carbon snaps onto helium to form oxygen, 16. So 12 to 16. Remember, helium has mass 4. So 12 plus 4 is 16. Then oxygen snaps onto helium. 16 plus 4, 20 to form neon. Neon plus 4, or 20 plus 4 is 24, or magnesium. So you see that you kind of, in a star, you're not producing all elements equally. Carbon, then oxygen, then neon, then magnesium are most common. Some of the other main ones are carbon hits into that oxygen you've been producing to form silicon. The oxygen hits into the fuses with the oxygen itself to form sulfur. Silicon fuses with silicon to form iron. So these are the most common elements because they're what happened mostly. That's what is hitting each other inside the core of one of these high mass stars. And at the end of the day, you're building up a core of iron because that's the one element. Well, that's the end point of this process where you can't fuse anymore. And what happens? Well, so remember, the thing preventing this big giant core of iron is called electron degeneracy pressure. Now, this is the same pressure that keeps normal. Just if you have a chunk of iron in your hands and you try to press on it, it doesn't shrink, right? It's solid. That's due to electron degeneracy pressure. Atoms don't like to push into each other. But once you get a core this massive in a very massive star, like say 25 solar masses, the gravity is so strong even electron degeneracy pressure isn't enough to prevent it from collapsing. Okay, so you have this catastrophic event. The atoms themselves collapse, and what's happening? Electrons orbiting the protons in the nuclei, they get absorbed into the protons. Now, an electron is negatively charged, a proton is positively charged. So if an electron gets absorbed into a proton, you produce something neutral. You produce a neutron. So this is why you get a neutron star. The atoms collapse, the electrons get absorbed into the protons, leaving behind a neutron and one of these forms of these rays we called the neutrino before. And this is an incredibly energetic explosion. This is one of the most energetic explosive events in the universe you can see even in other galaxies. Normally, you don't see individual stars in other galaxies. When this happens, when you get a supernova, suddenly you can see a star, even in a distant galaxy. And you leave behind a neutron star that is a giant core of just pure nuclear material. It's like a giant nucleus made all of neutrons. I introduced the weak interaction before. It's just kind of fun to show you. I don't expect you to know this other than just to appreciate that this is some cool physics showing the fundamental force that allows a proton to absorb an electron. So this is called a Feynman diagram. A proton is composed of a down quark and two up quarks. A neutron is the same thing as a proton, but one of the quarks has gone from an up quark to a down quark. And the way that happens is through this weak interaction process where the electron changes a quark from up to down and turns into a neutrino. So initially you have a proton and an electron, and on the right at the end you have a neutron and a neutrino. And this is a process at a fundamental level we understand by which a proton absorbs an electron to produce a neutron and an electron neutrino, and thereby an atom collapses. So proton and electron down to just neutrons, only neutrons. The neutrinos escape. Here's some examples of what's left behind after these catastrophic explosions. This is a supernova from the year 1006, so about 1,000 years ago. We call this a supernova. Ever since then, giant expanding shock wave, essentially, from that explosive event. At the center, you can't really see it, but at the center is what's left behind in the case. So here in the center, in the Crab Nebula, this is another one actually about 1,000 years ago, in 1054. This is a case where in the center, you have a neutron star left behind. We'll talk in a future lecture about some of the unique characteristics of neutron stars, where you can actually see, you can actually listen to them. They have a kind of an interesting repeating pattern that you sometimes see. It's called the pulsar. But in any case, in the very center, you have these things called neutron stars. And out here, you have this expanding kind of remnant of an explosion that itself becomes a nebula. It becomes something that's distributed with lots of heavier elements, because this was a massive star that produced all of these elements that are going to produce perhaps solar systems in the future with all the ingredients for life and all sorts of metals and interesting stuff, right? To produce planets with dirt and rock and metals and so on, carbon. Here's another supernova remnant. Now, supernovas are really brilliant. I mean, astronomers get really excited whenever there is one, and we see lots of them all the time, but they're usually very far away. Usually what we see is like, we have telescopes always pointing to the night sky, and we see a region where there wasn't a star, and then suddenly there is a star, and then it fades away. Here's an example where in 1987, this was kind of the last major supernova that was close enough to us that you could see it, with the naked eye. If you went out at night. And here's a picture of the sky where you see this bright supernova, and then 10 days later it's kind of shrunk to not being visible with the naked eye. So this is what happens. Just in the night sky, suddenly there's a very bright star looking object, but then it fades again. And at least that tells us, hey, we got to point our telescopes to that way, try to capture it. And here, and as you can see, this was 1987, so we're now a few decades later. We can actually begin to see the expanding kind of shell of what will become a nebula, and thousands of years from now, expanding away from that supernova. So it's actually really cool, and it'll be fun to watch this evolve over the next 100 years or so. I'll talk about the types of supernova in the next lecture. Okay, finally, here's just one more. This one's 40,000 years old, so you can see it's producing basically this. Well, we'll talk about these later. This is what we'll call a hot bubble. In this region, the interstellar medium is hot. It's heated up by the supernova, and so you're producing both stuff that will form a nebula, which is really useful for creating stars. We're also going to produce a region that is hot, and so is not good for creating stars because it'll actually make the interstellar medium in some places more diffuse because it's heating up. So, but anyways, this is kind of a very beautiful expanding kind of shell of material now pushing out against the interstellar medium from the supernova. And at the very center, you can't see it, but we'll talk about it in a future lecture, is a neutron star. Any questions about, we'll talk more about supernovas and stuff, but so far, any questions about neutron stars, high mass stars, supernova? Throat. It's getting scratchy, so I'm going to go very well. All right, so we talked about in the very beginning of the class something that I think is really neat, which is that we are made of the stuff produced in stars through the processes we just talked about. I pointed out in the beginning, the first day of class, that there have been ancient cultures. This one 1,000 years ago, they looked up in the sky and saw a recording of a supernova that they made on the walls of stone. It's called the petroglyph, recording the correct moon phase at the time. And wondered, right? They wondered what on earth this was. Looking out in the heavens, seeing these stars, and makes me wonder just looking out at the night sky. But we now know something just so amazing, that we literally are made out of stuff produced from stars. We wouldn't be here if it weren't for the elements produced in stars. Otherwise, all there would be hydrogen and helium produced during the Big Bang. Carl Sagan famously said that we are star stuff. He said the nitrogen in our DNA, calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. Carl Sagan, by the way, was an astronomer, but also a popularizer of science. He had the show Cosmos, or hosted the show Cosmos before Neil deGrasse Tyson did. It's great if you can watch it. It's kind of the first Cosmos, like most things, I think is better than the sequel. But it's true that most of the material from which we and the planet and so on are made were born inside stars that lived before our own solar system formed, right? Our own solar system formed from a nebula produced from some dying star. Okay, and we see, here's an example of the star stuff here. It's a nebula, right? We see these clouds in the interstellar medium. We see gas and dust that's star stuff. That's stuff that formed, whether as a planetary nebula from a low mass star, or supernova, high mass star. Okay, that's how you ever get planets, right? Planets are made of terrestrial material, meaning stuff heavier than hydrogen and helium, produced inside the cores of stars through the processes we've described. And so we talked about the curve of binding energy. Kind of this explains some of the first things you might think of with regard to where elements come from, right? It explains that inside stars, you're producing elements from hydrogen and helium up through iron and nickel. Okay? Right, inside the interior of a star, you're not producing anything beyond iron or nickel. As over the next few minutes, I'll talk about, one way of producing even heavier elements is through some of these very explosive processes, such as supernovae, because otherwise you can't form these heavier elements. And as a result, you expect them to be rare. We talked before. Let me see if I can go back. We talked before about these processes, right, that are most common: carbon, oxygen, and neon, for example, grabbing a helium atom. So carbon plus helium becomes oxygen. Oxygen plus helium becomes neon. You're going up in steps of 4. This is a general pattern that you actually see if you look at all of the elements by abundance, like in the Earth, right? In the Earth, you look at what percentage of the Earth's crust is made of carbon, nitrogen, oxygen, and so on. What you see is exactly what you'd expect from what's produced in stars. You see carbon, nitrogen, oxygen, right? Nitrogen, so carbon plus 4 becomes neon, plus 4 becomes magnesium, plus 4 becomes silicon, plus 4 and then oxygen collides with oxygen to become silicon. Silicon collides with silicon to become iron. So what you see is an abundance of elements. So those are the ones I'm kind of pointing to here, all produced through the most common processes inside that multiple shell fusion stage of high mass stars. Of course, hydrogen and helium are most common because they were produced during the Big Bang. Now, after iron and nickel, you see much less, right? So it's much lower in this picture. Are all these heavier elements, ranging up to gold and so on, silver, elements that are not produced inside stars in the same way, and so they're much less common. It's rare. Some of these are formed in supernovae. Our understanding is that some of these are formed in colliding neutron stars. So we just talked about how neutron stars form. That's just kind of like giant nuclei made all of neutrons. Well, it's very rare, but these things can collide and then distribute globs of this nuclear material all through the universe that then forms a range of these heavier elements that are therefore rare, because that's a rare process. Here's a periodic table, and when you normally look at the periodic table of elements, it's in the context of chemistry. So they've kind of created this periodic table where each column represents something with a certain chemical property. Right here on the left, these are called the alkali metals. Here on the right, these are called the noble gases. Right, alkali metals are very reactive, but noble gases are not reactive, and so on. But here's a periodic table that's very different. It's just showing where these elements came from. So the main takeaway is that hydrogen and helium mostly just come from the Big Bang. But everything else, so if I highlight with my mouse, kind of all the way up, a little bit past iron, most of the stuff that the Earth and we are made out of is all stuff produced in dying stars. Okay, and then everything else, what's kind of yellow and well, the stuff that's orange is stuff that's produced either in supernova or colliding neutron stuff. Because that stuff is rarer because it can't be created in dying stars. It has to be produced either in this catastrophic explosion of a supernova or in this rare event when neutron stars come from. And it's therefore rare to see stuff much heavier than that. synthesis of PHYS. Oh, I guess. Hopefully this is an easy one for you then. So what did Carl Sagan mean? He said that we are all star stuff. More seconds.
That one, right? Not Big Bang. That's the only thing. Big Bang.
Okay, and then I'm glad that most of you got that right. Yeah, he meant that the carbon, oxygen, and all the other elements essential to life, pretty much everything on Earth that has, a large quantity of Earth's crust, it's all made by nuclear synthesis. So, iron, carbon, oxygen is made in nuclear synthesis. So, of course, other stuff like gold, stuff heavier than iron, but still produced. It's still star stuff, but it's produced usually in a supernovae or colliding neutron stars, that sort of thing. It's something that has to be produced more rarely. It can't be produced through fusion. All right. We could go on to the next lecture, but I think this is an appropriate place to stop today. Are there any questions on high mass stars or low mass stars? Or star stuff? All right, everyone, have a good week. Thank you, Professor.
Thank you.